Hi everyone! Today we're going to be talking about inverse relations and functions. Our objectives for today are that students will be able to find the inverse of a function or relation and determine whether two functions or relations are inverses. Let's get started. Alright, when we're talking about inverse relations, the important thing to know is the notation and how to find it. So, the inverse of a relation is written as, we write it as capital R to the negative 1 power, and we read this as the inverse of the relation. To find the inverse of a relation, all we need to do is switch the x and y values. And we will walk through examples of how to do this. With inverse relations, what we want to know is it a one-to-one relationship? And a function has a one-to-one relationship if the relation and its inverse are functions. So let's take a minute to write this down. A function has a one-to-one relationship if the relation and its inverse are functions. And what this means is if it's a function, that means that the x values do not repeat. They do not, emphasis on the not, repeat, and that makes it a function. Alright, so let's go through a couple examples and see what this means to us in a real life problem. Alright, so number 1, we're given this relation right here, set of points, alright, and we want to find the inverse. So to find the inverse, take each ordered pair and switch the x and y values. So the inverse of this function, we write our brace, and then switch the x and y values. So then becomes -2, +1. Then in the second ordered pair, it becomes 4, 2. Third pair becomes -1 and 3. We're just switching the x and y. Then it becomes -2, +4. And this is the inverse of our relation. So then we want to ask ourselves, our original relation, is it a function? Do any of the x values repeat? And the answer is no. So none of the x values repeat, so yes, it is a function. Then we want to look at our inverse. So this is the inverse of our relation. Do any of the x values repeat? The answer is yes. -2 happens twice in our x as an x coordinate. So no, this is not a function because the x values repeat. So is the relation one-to-one? The answer is no, because the relation and its inverse both have to be functions in order for it to be one-to-one. Alright, number 3, you could also see it written as a map like this. We call this a map. This relation is a map, and these are your x values, these are your y values. We're saying x is 0, y is 6, x is 1, y is 2, x is 11, y is 6. Those are our 3 points of our relation. So if it helps, write out the ordered pairs. So we've got 0 and 6, we've got 1 and 2, and we've got 11 and 6. Then if we want to write the inverse of this relation, switch the x and y values. So the inverse of this relation would be 6, 0, 2, 1, and 6, 11. Then we want to look, is our original relation a function? Do any of the x values repeat? The answer is no, they do not repeat. So yes, it is a function. Then we want to look at our inverse. Do any of our x values repeat? The answer is yes. We've got 6 repeating. 6 occurs twice as an x value. So no, the inverse is not a function. Therefore, because they're both not functions, the relation is not one-to-one. All right, another thing we're going to be learning about is the horizontal line test. So I want you guys to recall or remember that the vertical line test is used to determine whether a relation is a function given the graph of that relation. All right, we learned about the vertical line test earlier in the year. All right, that's how we can tell if it is a function. So the horizontal line test is used to determine whether the inverse of a relation is a function. All right, so we can use the horizontal line test to tell us if the inverse is a function. All right, so both the relation and its inverse must be a function in order for it to be one-to-one. All right, we just learned about that. So here's an example. Number 4, we want to determine whether the relation shown presents a one-to-one function. So it has to pass both the vertical line test and the horizontal line test. So vertical line test, if we were to draw a vertical line, it can only touch the graph at one point. So if we were to draw vertical lines, it's only touching our graph at one point. So it passes the vertical line test. If we were to draw horizontal lines, it only touches the graph at one point. So it passes the horizontal line test. Therefore, because it passes the vertical line test and the horizontal line test, yes, this graph or this relation is one-to-one function. Now number 5. First we want to see if the relation is a function, so we want to test it using the vertical line test. Only touches the graph at one point, only touches the graph at one point, only touches the graph at one point. Now it has to pass the horizontal line test for its inverse to also be a function. So if we were to draw a horizontal line, it can only touch the graph at one point. However, with a horizontal line, it doesn't pass the horizontal line test because this horizontal line touches the graph at 3 points. Therefore, the inverse of this relation is not a function because it does not pass the horizontal line test. So we say no, this relation is not a one-to-one function. All right, now when we're talking about inverse functions, the notation for the inverse of a function of f of x is written as f of -1 to the x, and we read this as the inverse of f of x, the inverse of our function, all right? But it'll always be written like this. And to find the inverse of a function, the first thing you want to do is take your f of x and replace it with a y. Then you want to switch your x and y. Then your third step is to solve for y. And then last but not least, rewrite your y as the inverse of the function. So as f of -1 of x. Okay, we rewrite it looking like this. So let's do a couple examples of this. All right, so for number 7, we want to find the inverse of this function. So our first step is to replace the f of x with y. So now it becomes y equals x minus 7. Then the second step is to switch the x and the y. So switch them around and rewrite the rest of the function exactly like it is. Then we want to solve for y. So we want to get y by itself. Add 7 to both sides. These will cancel out. X plus 7 equals y. Or we can rewrite this as y equals x plus 7. And then our final step is to rewrite our y as the inverse of our function. So the inverse of f of x equals x plus 7. And that's our final answer. All right, number 9. First step is to replace f of x with y. So we replace f of x with y, rewrite the rest of the function exactly how it is. Then we want to switch our x and our y and rewrite the rest of the function exactly how it was. Then our goal is to solve for y. So we want to get y by itself, so the first thing we want to do is subtract 1 from both sides. X minus 1 equals -2/5 y. Then to get y by itself, we want to multiply both sides by -5/2, because then that will cancel it out. All right, so these cancel out. Now y is by itself, but we have to remember to distribute to both terms on the left side. So we get negative 5 halves x plus 5 halves equals y. Now we can rewrite this as y equals negative 5 halves x plus 5 halves. And then our last step is to replace y with the inverse of f of x. And then copy the rest of our inverse of our function exactly how it is. Oops. All right, so this would be our final answer. That is the inverse of our function. All right, number 11. First step, replace f of x with y. So we've got y equals x plus 4 to the third power minus 6. Then we want to switch our x and y. Rewrite the rest of the equation exactly how it is. Now our goal is to solve for y. Get y by itself. So add 6 to both sides. Now to get y by itself here, we want to take the cube root of both sides to cancel out that square, that cubed. All right, so that'll go away. We're left with the cube root of x plus 6 equals y plus 4. Subtract 4 from both sides. We're left with the cube root of x plus 6 minus 4 equals y. Then replace your y with the inverse of f of x, the inverse of the function. And we know the inverse is the cube root of x plus 6 minus 4. And that's the inverse of your function. All right, we also want to be able to verify inverses using the composition of functions. So we got to recall using composition of functions, all right? So f of g of x or g of f of x. So two functions, f and g, are inverse functions if and only if f of g of x equals x and g of f of x equals x. So let's see exactly how to do this. So in order for us to determine whether the pair of functions are inverse functions, we're going to use composition of functions. So we know that f of g of x has to equal x, and g of f of x must equal x as well. So let's start with f of g of x. So when we're dealing with composition functions, we say f of, and then plug in g of x. So g of x equals x minus 4, or x over 4 minus 5. Then we want to take our f of x function, and every time we see an x, plug this in for x. So our f of x function equals negative 4. We see an x, so plug in x over 4 minus 5. Back to our f of x function, it's negative 4x plus 5. Now we're just solving. So we want to distribute the negative 4 to both terms here. So we get negative 4x divided by 4 plus 20 plus 5. Negative 4x divided by 4 gives us negative 1x plus 20 plus 5. So x plus 25. Now, this does not, or it should be negative x minus 25. This does not equal x. So we know that our composition of f of g of x does not equal x. So, no, we can automatically tell that no, these are not inverses. You don't even need to do the composition of g of f of x, because right off the bat, we know that f of g of x doesn't work, so they are not inverses. All right, in order to prove that they are inverses, you would need to do both both f of g of x and g of f of x, and your final answer needs to be positive x. All right, the last thing we're going to be talking about today is graphing inverses. So if you're given that triangle ABC is formed by these 3 points in this relation, the first thing you want to do is write the inverse of this relation. So we know the inverse of this relation would be, take each point and switch the x and y. So it'd be 6, -1. Oh, not -7. It would be positive 2, -7. And -3, -5. So then you have the relation and the points that are the inverse of the relation. The next thing you'd want to do is graph the 3 points in your relation, triangle ABC, and the points that represent the inverse. And then we're going to see what you notice about this graph. So let's go ahead and do that now. So let's graph our original relation. So the points are -1, 6. So -1 up 6. There's our first point. Then we've got -7, 2. So 3, 6, 7. And then up 2 is going to give us this point. And then we've got -5, -3. So to the left 5, down 3. All right, and then we want to connect the dots because we know this forms a triangle. Then let's graph the inverse of the relation. So the first point is 6, -1. So we go to the right 6, down 1. Then our second point is 2, -7. So to the right 2, down 7. There's our second point. And then our third point is -3, -5. So -3, -3 is to the left 3, down 5. There's our second point. And we know this is also going to be a triangle. So connect the dots and form a triangle. Now, what I want you to notice about this graph is that it is reflected across the x-axis, or across y equals x. So y equals x is the line that goes up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, down 1 over 1, down 1 over 1, down 1, down 1 over 1, down 1 over 1. So it's this line right here, all right? And I apologize if that's not the straightest line in the world, all right? But anytime we're graphing the relation and its inverse, it's always going to be reflected across the line y equals x. So if we were to draw y equals x, that would be our mirror. We're always going to reflect the graph across that line, across y equals x. All right, so we take this point. If it's this way too, it becomes this way too. Over here, we're reflecting it across that line. This point, we reflect it across that line. Y equals x becomes our line of symmetry or our mirror anytime we're graphing inverses. All right, so let's do a couple more examples of this. All right, so the directions for number 1 are to find the inverse of each function. So we're going to first find the inverse of each function by replacing f of x with y, switching x of y, and then rewriting it as the inverse of the function. Then we want to graph both functions, both the original and the inverse, on our graph and verify that it is an inverse relationship because it should be reflected across the line y equals x. So let's do that with problem number 1. So f of x equals 2x plus 8 is our original function. Now we want to find the inverse of this. So we're going to rewrite, oops, I need my pen, not the highlighter. We want to rewrite this as y equals 2x plus 8. Then we want to switch x and y. So it becomes x equals 2y plus 8. Now we want to get y by itself, so subtract 8 from both sides. Divide both sides by 2. So we're going to end up with y equals 1/2 x minus 4. Then we want to replace our y with inverse of the function equals 1/2 x minus 4. And that is our inverse of our function. So, first thing we want to do is graph our original function. So, it's in y equals mx plus b form, right? It's in slope-intercept form. So, when we're graphing this function, I'm going to zoom in. All right, we're graphing 2x plus 8. So, the plus 8 tells us our y-intercept. So, we know it's going to cross the y-axis at 8. So, 4, 8. So, there's our y-intercept. And the 2x, the 2 tells us our slope. So, we're going to go up 2 over 1. Or in the other direction, down 2 to the left 1. Down 2 to the left 1. This is represented by our slope. So, we continue to draw points. And if you have a ruler, connect them with a nice straight line. I'm going to do my best here. And there's our original function. F of x equals 2x plus 8. Now we want to graph the inverse of this function. So the inverse of the function is 1/2 x minus 4. So the negative 4 tells us it's going to cross the y-axis at negative 4. Then the slope of 1/2 tells us we're going to go up 1 over 2, up 1 over 2, up 1 over 2, up 1 over 2. Down 1 to the left 2, down 1 to the left 2, down 1 to the left 2. And use your ruler to connect this with a nice straight line. I'm doing my best on here. I'm sorry, guys. All right, and there's the inverse of our function. 1/2 x minus 4. Now, if you were to draw the line y equals x, right, it would be this line right here. We know it goes up 1 over 1. So this is our line, y equals x. We can verify that this is an inverse relationship because our red line is reflected across y equals x, and that gives us our blue line. Our graph is reflected across y equals x. Therefore, we can verify graphically that this is an inverse relationship. So when you're graphing, you need to graph the original function, the inverse of the function, and y equals x.